In this class, we are going to discuss about the expression of kinetic energy and potential energy of a simple pendulum. Okay, and to discuss about the kinetic energy and potential energy of simple pendulum, we first know what is simple pendulum. If a heavy mass is attached to one end of a string, and this is light string, okay, and another end of this string be fixed in the vertical plane, then the motion of the heavy mass, or it is generally said to be bob of the pendulum, is known as simple pendulum. Okay, so we first try to draw a rough sketch of simple pendulum. This is the fixed end, and here the particle is attached, and let the mass of the particle is m, so weight is mg. Okay, and this is the vertical position, and let it be the fixed point O, and then this pendulum moves like this and makes a circle in the vertical plane. Okay, let these two are two extreme points. These two are two extreme points of the pendulum. Okay, where this is A and this is A dash, and let this is the angle alpha. Okay, and let P be any position of the particle at any time t, and in this case this is the bob, and in this case we write here along the vertical direction mg always act, and in this direction, and this is the tangent at the point P. Okay, this is the tangent at the point P, and let this is P, and if this angle is theta, then clearly this is also theta, and the component of mg along the string is mg cos theta, and this angle obviously pi by 2 minus theta, so the component of mg along this direction is mg cos pi by 2 minus theta, so this is mg sin theta. Okay, and if we draw a horizontal line through P, this is the horizontal line through P, let it cut the vertical line at P dash. Okay, so from the triangle OPP dash, clearly this is L. If L is the length of the string, O, this is the lowest point, let it be O dash. Okay, O dash, that is length of the string. This is let be L. Okay, and clearly from this triangle OPP dash, this is L cos theta, because this is theta, so here we write OP dash, this is L cos theta. Okay, now we consider the motion of the particle at any instant t. Here we let P be the position of the particle, and in this case here another extra point we have to mention must here. This is the tension of the string, and in the mean position here, that is in the vertical position, T, tension on the string, this is equal to weight of the bob or weight of the mass. Okay, and if we consider here tension always act on the fixed point, and in this position here T or at P, T this is equal to mg cos theta. Okay, and if we consider the tangential acceleration, what is the tangential acceleration? Tangential acceleration is given by d2s by dt2. Now we consider O dash P. This is the arc, this is S. Okay, and since this is theta and this is the radius of the circle L, so we must get S, this is equal to L theta, because arc, this is equal to radius into angle. Okay, so from here we get d, we first differentiate with respect to t, ds dt, this is equal to L theta dot, and this is d theta dt, and the second derivative is d2s by dt2, this is L d2 theta by dt2, or it is denoted by L theta double dot. Okay, now we put the value of d2s by dt2, this is given by L theta double dot, and which is given by is equal to this acceleration along tangent to the particle, and we draw the tangent of the particle, and tangential force always act along this line, and the amount is mg sin theta. So we put here mg sin theta, and also we multiply by m here because mass of the particle, so this is mf, and this is also the force, and here also a negative sign must be added because this force try to decrease the angle theta. Okay, so we get the equation of motion as L theta double dot, this is equal to minus g sin theta, so theta double dot, this is equal to minus g by L sin theta. This is the equation of motion of a simple pendulum. Okay, and from here we get, if theta is very small, then in this case theta double dot, this is equal to minus g by L into theta, because for small theta we know that sin theta is nearly equal to theta from the infinite expansion of sin theta, and this is the equation of simple harmonic motion. Okay, so for this reason we say that the motion of a simple pendulum is simple harmonic motion with period of oscillation is 2 pi by root g by L, and this is given by 2 pi into root over L by g. Okay, this is one part of this topic. Now we discuss about the kinetic energy. How to find the kinetic energy? The kinetic energy of any particle in motion is given by, kinetic energy is given by half mv square. Okay, so we have to find the value of velocity v. Now if we multiply this relation by 2 into d theta dt, then we get 2 into d theta dt into d2 theta by dt2. This is given by minus g by L into sin theta into 2 d theta dt. Clearly the left side is ddt of d theta dt whole square, and the right side is minus 2 g by L into sin theta d theta dt. Okay, this is d theta dt. Now from integrating we get d theta dt whole square, this is equal to minus 2 g by L into sin theta d theta. This is the integration, and integrating we get the result as d theta dt, this is dt whole square, this is given by minus 2 g by L into cos theta. This is plus because integration is minus cos theta plus another constant c. Okay, so we have to find the integrating constant by using appropriate initial condition. Here we take the initial condition as this, where theta, this is equal to alpha, then velocity v equal to 0, and in this case theta dot equal to 0. Okay, because this is the maximum point where the bob start to move. So we put theta dot equal to 0 where theta equal to alpha. Okay, so we get the result as C, this is equal to minus 2g by L into cos alpha. Now we put the value of C here, we get the result as theta dot square. This is theta dot square, this is 2g by L into cos theta minus cos alpha. Okay, now we here use an important relation of particle mechanics. The first is radial acceleration. What is the radial acceleration? Sorry, radial velocity. Radial velocity. Radial velocity is given by r dot, and cross radial velocity. Cross radial. And we know that the expression of radial velocity or notation of radial velocity is Vr and cross radial velocity is V theta. This is r theta. So we get the resultant velocity of the particle at the point P by using radial and cross radial velocity. And the resultant velocity here we write this is V. This is given by root under V r square plus V theta square. Okay, that is V square, this is equal to VR square, means r dot square, plus this is r theta dot whole square. Okay, and for this motion here r, this is given by r is given by L. This is constant, this is the length of the string, and clearly r dot, this is equal to 0. So we get here from this result, this is 0 plus this is L square into theta dot square. Theta dot square we already derived here. This is given by 2g by L into cos theta minus cos alpha. Right? So we get 2gl into cos theta minus cos alpha. This is the expression for velocity of any point of the particle. Okay, now we know that the expression of kinetic energy, which is given by half m v square, and this is half into m into, we put the velocity of v square. From this result we get this is 2gl into cos theta minus cos alpha. So mgl into cos theta minus cos alpha. Okay, so this is the expression of kinetic energy of the simple pendulum at any point P. If we put theta, this is equal to 0, then the kinetic energy of the pendulum at the lowest point, that is at O dash, we get from here. Okay, and if we put theta equal to alpha, then we get the kinetic energy of the pendulum at the highest point A, and clearly kinetic energy at O dash, which is given by putting theta equal to 0, is given by mgl into cos alpha. A negative sign is here. Okay, and kinetic energy at A, this is the highest point, and this is given by, if we put theta equal to alpha, then we get kinetic energy at O is 0. Okay, now we concentrate towards the potential energy. The expression for potential energy is, we know that mgh, where h be the vertical depth which moves by the particle. It is clear that this is the vertical depth or maximum vertical depth, and when the particle at P, then the vertical depth is this. So here we have to find the value of P dash O dash. Okay, and so we write here mg into h means P dash O dash, so we write O dash minus O P dash. And what is the value of O dash? This is obviously L, this is the length of the string, and the value of OP dash, which is given by, we already write here, L cos theta. This is the base of the triangle OPP dash. Okay, so this is L cos theta, and taking common MGL into 1 minus cos theta. Okay, so the potential energy at P is given by this. Okay, so we get kinetic energy. This is the kinetic energy expression, and this is the expression of potential energy. Right? Now, for this case, if we put theta, this is equal to 0, and in this case the particle is at O dash, and here potential energy, this is equal to 0. Okay, because theta equal to 0, this means 1 minus 1, and at theta equal to alpha, where at that point, that is at A, then potential energy is given by mgl into 1 minus cos alpha. Okay, now if we add kinetic energy plus potential energy at P, this is given by half mv square plus mgh at P, and this relation gives, this is the kinetic energy relation, this is given by mgl into cos theta minus cos alpha, plus this is given by mgl into 1 minus cos theta, So clearly cos theta and cos theta cancel out, so we get mgl into 1 minus cos alpha, and clearly this relation is free from theta, that is, this relation is constant for any instant. Okay, and we know that, or we say that kinetic energy plus potential energy at any point is equal to constant. So we say that the conservation of energy is held by the simple pendulum under gravity, and this is the free motion because there is no resistance force act or no resistance force present. Okay, very important topic, and this is the kinetic energy and potential energy, and this is the conservation of energy. Thank you for watching.